Everybody, let's give this problem a try. So there's a block sliding on this ramp over here. It's frictionless. Then there's a block hanging over here. And then there's a pulley. Then when I was reading this question, I'm like, what is this inner radius and outer radius? So just looking at that pulley. But then when I zoomed way in, the picture is not very high resolution from the book, but you can see how this cable goes to this inner radius right here. And then this other cable goes to this outer radius over here. So that's what it means. I didn't really notice until I zoomed all the way in. Okay, so that means, let's draw the free body diagrams. So there's this block over here. So there's normal force, tension in this rope over here. And then it has weight. I'll just call this mass 1 and mass 2. Okay, and then normal force, and then tension. I'll call this tension 1. That's connected to block 1. And then block 2, we'll draw it over here. There's the rope here, so I'll call that tension 2, connects to block 2. And then it has weight. And then for the pulley, let me get some help here. Okay, so then there's the inner radius and then the outer radius. Okay. Okay, so then the free body diagram, this rope is connected to the inner radius over here. But then this one is connected to the outer radius over here. So this is T1, this is T2. And then see how the pulley is rotating about some bearing. So then there's some normal force. We're not sure which direction it is. Normal force for the pulley. And then the pulley itself has weight. So whatever the weight of the pulley is. Weight of the pulley. Okay, so we have our 3 free body diagrams. Okay, so let's go for this one. Oh, let's pick coordinates. So I'm not sure if this block were heavy, then it will go this way, and then this block will go up the ramp. If this block were sufficiently low in mass, then it will go up, and this one will go down. But if it's just the right mass, then it'll keep the pulley from rotating. So that's what we're looking for, to prevent any motion. So it doesn't really matter which way I pick coordinates. Let's say if I pick like this. And then, so let's say if I think this block is going to go up the ramp and this block is going to go down, and then the pulley will rotate, let's say in the z direction. Let me pick coordinates here. If I say this is x and this is y, then z would be this way into the page. Okay, so for this free body diagram, let's take a look at the picture. The angle is right here, which is right here, 30 degrees. Okay, so in the x direction, we got T1 minus the x component of that, m1g sine theta, equals mass 1 times acceleration, the x component of acceleration, and the y direction, n minus m1g cosine theta equals m1ay. However, we're looking for the condition where it's keeping it from rotating, so it's not going to move. So the velocity is 0, so definitely the acceleration is 0. Ay would be 0 no matter what, because it's moving. It would only move in this direction. But we're looking for the case where ax is also 0. Okay, and then let's do this free body diagram. I'll just write it here where there's space. In the x direction, m2g minus t2 equals m2ax. And then again, we're looking for where ax is 0. Let me number these equations. Okay, so we got 3 equations. And now for this free body diagram, let's sum torque about any point you want. So you could sum torque about over here, or say over here, or over here. Those would be clever choices, because if you sum torque about right here, this force wouldn't provide any torque about this point. If you sum torque about here, this force wouldn't provide any torque about this point. But then if I sum torque about here, neither of these would provide any torque about this point. So I think that's clever. So about the center of the pulley, about its center of mass. Okay, so then there's no torque from this, no torque from this, only from T1 and T2. Okay, and then the torque about this point here from T1 would be, see this lever arm right here? That cross, well, this vector cross this vector, but those would be perpendicular. So it's just here to here times T1. And that would go this way in the counterclockwise direction, which is actually in the negative z. So it's negative r T1. Okay, that's the torque by this. The torque by T2, the lever arm is, also this is the inner radius, right? So I'll just call it I for inner. Okay, and then the torque by T2 is this lever arm right here, cross, well, this vector cross this vector, but those are perpendicular, so it's just this times this going clockwise, which is in the positive z direction. So plus r, the outer radius, T2, equals I alpha. Which I? Because I summed torque about the center of mass, this is the moment of inertia about the center of mass. However, we're looking for where the pulley is not rotating, so where there's no angular acceleration. Okay, so we have these 4 equations. What are we trying to solve for? The mass. Okay, so for these 4 equations, what's unknown? Okay, so T1. Okay, we know mass 1, right? That's 5 kilograms. We know the angle. Okay, we don't know this. We don't know this or this. The radius is 20 centimeters, 30 centimeters. Okay, so we got those. And then this equation, we don't know the mass or this tension. Okay, so unknowns. T1, T2. The normal force. M2. Okay, so we got 4 unknowns. But we have 4 equations, which means we can solve all 4. We only really, in which order would you solve these? Right, look. Equation 2, you can solve for n. Got it. Right, got it. Equation 1, solve it for T1. Solved. Right, then you have T1, plug it in right here. Then you got T2. And then you have T2, plug it in over here, and you have M2. So then we have all 4 unknowns, just like that. Okay, but let's do a little bit more work. So that was me kind of explaining the concept. Let's get the actual answer. So let's see. I definitely need equation 3 because that has M2, which is what I'm after. And then I need T2 right here, which the only place that shows up is here. But then I need T1, which is here. Okay, so let's take this and put it there. So I'll do that first. So 1 into 4. Okay, so T1 is m1g sine theta. And then you take that answer and put it there. Right, so T1, so it's minus Ri times T1, which this is T1, plus Ro T2 equals 0. Okay, and then if you look at this, we can solve this for T2, right? So T2 is Ri over Ro m1g sine theta. And then this goes into equation 3. Here, let me copy equation 3. I will literally just copy it and paste it where I have more space over here. Okay, so this is equation 3. This entire side over here is 0, right? Right, so T2, so M2 equals T2 over G. Right, so then, and then T2 is right here. So just this divided by G. And there we go. So whatever what was it again? 20 centimeters, 30 centimeters, 20 centimeters, 30 centimeters. M1 was 5 kilograms and the angle's 30. 5 kilograms sine 30. Sine 30 is 1/2, right? So, right, so it's going to be so 2/3 and then 1/2, so 1/3 of 5. So whatever, 5 over 3 kilograms. There's your answer. Okay. Is that the question? Okay, so hopefully that was helpful. Let me know if you have other questions. I'll see you on the next video.